Hello, my name is pvquero, and today I'm going to present my project in casting processes. Okay, so basically I will be talking about three different types of projects, and each of them I will talk about the material selected, the part I'm designing and the process to design it, the advantages and drawbacks of the processes used, as well as their solidification processes. Okay, so the first project is about airspace and high altitude missions. Okay, so the material selected for this project was titanium aluminide. Basically, it is widely used in aerospace industry due to its high strength and low density. I chose to use it in a turbine blade, which I will explain later, because they need to support high temperatures from the combustion chamber. And also, as they are in contact with air and gases, they need to be good at corrosion and oxidation. So now, as I said, I'm going to use a turbine blade of titanium aluminide, and to do so, I will perform an investment casting with a ceramic mold. I think this is the most appropriate technique, as it is really good to perform complex shapes with tight tolerances. And also I decided to use the ceramic mold because it has a high thermal stability and because it is good to incorporate some cooling channels that may reduce the apparition of porosity and shrinkage during the process. So now here there is an image. This is the turbine blade. It's not a very good drawing, but the first thing is to have a wax pattern that will be attached to a tree. um, Now we include here the ceramic, molten ceramic, to perform the mold. And once the mold is done, which is drawn here in blue, we will introduce the titanium aluminide, which is molten. And after some time, while it is cooled, finally we have the structure and we can deattach our turbine blades, which are finally created. Okay, so one important advantages of this process is that complex shapes can be produced with precise details. This is important because we usually in turbine blades need to have a design angle in order to avoid shock waves due to high incidence Mach numbers. Then also surface finish is also important in order to avoid, for example, boundary layer separation um, of the flow. This method is also compatible with high melting point alloys as titanium aluminide. However, some drawbacks is that it is very time consuming. As you saw, there are many steps, and it's also labor intensive, which means that we need to have people performing the task and people which is qualified. It is also high cost, and both ceramic cores and wax patterns are delicate and fragile and may break during their operation while handling them. So a solution, we cannot do anything with cost or time, but we can have qualified workers to avoid breaking those cores and to perform the task as fast as possible. Okay, so now talking about solidification, we need to highlight that there are not many defects of porosity or shrinkage due to the ceramic core that we are using. And the main structure of the solidification can be seen here. Firstly, we have this chill zone, which is caused by the quick decrease in temperature. Then we have these elongated grains that finally reach to the equiaxed zone. So basically the main process followed is nucleation of the grains, then the growth of those grains into the solid, and finally the final solidification. And here we can see a temperature versus time graph in which we can see that the solidification time from the purine temperature up to the solid stage, which is already this one, solid. Now the second project is based on automotive and high speeds. So I'm basically choosing the carbon fiber reinforced polymer with some resins. Basically, carbon fiber is the most used material in Formula One. This is because it has a high strength to weight ratio. Weight is crucial in Formula One in order to improve the lap times. Then we need it to be corrosion resistant against air, against water. It needs to be stiff and rigid. Fatigue resistance also because we are subjecting it to many cycles in a F1 car. Finally, carbon fiber is crucial also because it can be easily modeled into complex shapes such as ailerons, which is the part I have chosen. I chose this part because it is fundamental in the aerodynamics of an F1 car. The process I chose was resin transfer molding. So basically, the main steps are making the mold, which is reusable in this case. Then we need to fabricate the preform, which is only those carbon fibers. Then we should close the mold, which we are going to use, and inject the resin. And finally, we should let it cure for some time. And after it has been cured, we should demold and perform some finishing. In this case, I chose to perform some surface coating to repel water because if water is stuck in these parts, it can have it can produce drag by increasing the boundary layer separation, forming important decrease in the speed. So now here we can see the drawing. Basically, we start with the preform manufacturing. Then we create the form we would like to have, and we close the mold. We inject the resin over here, and we let it cure for some time. And after that, we just take the mold out and perform the final processing of water repellent. The advantage of this process and carbon fiber is that carbon fiber is lightweight and durable. Then the reusable mold is crucial because pilots tend to break a lot their ailerons in the races or in the qualifications. Then we have also the design flexibility. We need to be able to modify slightly the aileron over the season. In this case, to try to beat Max Verstappen. However, we have Fernando Alonso, which will be able to do it this year. Then some drawbacks. The initial investment of this technique is really high, as well with the normal cost, and it is also a complex process as you have just seen. The solution, money is not an issue, as they already have a lot of machinery to perform these things and many sponsors. And finally, the complexity. It can be tackled with high professionals that can take care of the resin injection, the curing parameters, or the mold design. Now talking about solidification, basically the resin will start as a liquid and will fill the cavity of the mold, in which it will start to react with the already pre-existing material. This chemical reaction needs to be in presence of heat and pressure. And then in the curing process, which is where solidification occurs, um, the transition from liquid to solid state will cause the formation of a polymer matrix, as you can see here, in which the black dots are the carbon fibers. Porosity can be tackled easily during the injection of the resin through vacuum, as it will remove trapped air. Finally, the shrinkage it cannot be stopped, so it needs to be tried to be optimized as good as possible during the mold design and as well as the resin that we are going to use. Okay, so now the third process is a process for marine and deep depths. So in this case, I was also going to choose the titanium aluminide, but in order to not repeat myself, I decided to use a nickel-based superalloy. This superalloy is highly resistant to corrosion, which is the main property we need to have in this case. As well, it is very strong and tough, and it's also very used in marine applications. And another important thing is that it is great at a high variety of temperatures. Usually marine temperatures are low, but we may encounter some uh, fluctuations in the temperature. So this material will be great in that case. Okay, so now about the part and the process I chose, I decided to perform a pressure-resistant housing for electronic instrumentation. This is basically a rectangular or cubic cage where we can store some electronic devices. I chose also sandcasting because I think that the shape is simple enough to be performed with this process, which obviously cannot be used with really complicated shapes. The process of sandcasting is very straightforward. First, we need to create the pattern, and we also need to put the pattern in the sand mold. Then, after we've put those parts, we need to remove them and put them together in the mold cage, which is this black structure over here. We'll put one over the other, and we start to pour the the material, the nickel superalloy, the molten nickel superalloy. And here you can see how chills are included, some external chills, which basically help to increase the solidification, the cooling rate, sorry. And finally, once it is already solidified, we just need to take off the mold, and we will have our cage manufactured. The main advantages of this process is that sandcasting is a good process for creating internal cavities with cores. So in this case, that we are performing just a simple box to include inside some electronic devices, um, is great. Is an easy form. Then production will be low as it's for a very particular application. And finally, it is the material compatibility is also important, as sandcasting can withstand materials with high melting temperatures, which is the case of this superalloy. The drawbacks of sandcasting are well known. The first one is the rough surface finish. Uh, Another one is the dimensional accuracy. However, this is not going to be an important issue in our case because the shape is going to be really easy. Then also porosity and inclusions. In the surface, there may be some defects, or inside the material we can have microporosity. And another drawback about sandcasting is that the molds are not reusable. some solution. For the surface, the rough surface, we can perform some machining or grinding in order to polish it. And then against those micro defects, we can perform visual inspection. And for inside defects such as microporosity, we can also perform some ultrasonic tests. Okay, so finally about solidification. We have, as I just said, that the surface defects can be detected visually and micropores can be detected using ultrasonic tests, which basically you perform a signal and you measure the time it takes the signal to come back in order to detect whether there is a pore or not. And finally, you can see that I drew the temperature versus time graph, and there is the use of chills accelerates cooling, which means that the slope is greater in this case. And so solidification time is widely reduced in comparison, for example, with the temperature versus time graph that I showed in the titanium aluminum case of the aerospace process. So this is the end of my presentation, and I hope you enjoyed. Thank you.